So in this section, we're going to look more at the arithmetic of matrices and adding and subtracting them and their elements. So the rows and columns are still the same. Dimensions are still the same. And the things inside the matrix are called elements. So, again, just to review, these are the rows, 1, 2, 3, da, 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 all the way down to whatever. These are the columns. And we write, if this is called matrix A, then all the elements inside there, we use a little lowercase a, and we do I, J. The IJ tells us the I is for the row, J is for the column. Because remember, it's always the row for the dimensions by the matrix. Nope, sorry, not the row by the matrix, the row by the column of the matrix. So it says, what are the values of the elements in the matrix? So if I go down here and write them, so A11, row 1, column 1 is -2. A11 is -2. A21, row 2, column 1 is -3. A row 1, column 2, row 1, column 2 is -1. And A22, second row, second column. So you need to be able to identify, based on location, the value that coincides with that location in the matrix. So if we are going to add and subtract matrices, we are going to add and subtract things in their respective places. Just like if you were to add and subtract expressions, you would put x's with x's and y's with y's. You put things that are similar together. Something that is worthwhile to note. So I have matrix A, matrix B. There's some order M, N, then the sums is the NM matrix where you add the pieces together. The two sums of the matrices of different orders is undefined. So what that is really saying, this piece right here, is that the order, the M by N, the dimensions, that's another word to say it, dimensions, of the matrices must match to add or subtract them. So I always make sure that my dimensions match first. So if I go down to the first problem, the first one is a 2 by 2 matrix and a 2 by 2 matrix. So when I add them together, I'm still going to be a 2 by 2 matrix, and the things that you add together are in coinciding places. So if I'm adding this plus this for a 0. 2 plus 3 for a 5. Row 2, column 1, 0 plus -1. And then row 2, column 2 plus row 2, column 2 makes a 3. And this right here is your answer. On the next one, this is a 2 rows by 3 columns. So this is a 2 by 3 plus a 2 by 3. So this equals a 2 by 3 matrix, which is going to look like this. And so this spot here would be called A row 1, column 1, A row 1, column 2, A row 1, column 3, and then we're going to add those pieces together. This is A row 2, column 1, A row 2, column 2, A row 2, column 3. And we add the pieces in the respective places together. So for this one, red with red is a 0. Blue with blue is a 2. -4. Do red. I'm gonna run out of colors. Gray with gray is going to make a 6. Yellow with yellow is going to make a 2. Black with black will make a 6. So this whole thing is our answer. If we look at the last one, this has 2 rows and 1 column. So it's a 2 by 1. This one has 2 rows and 2 columns, so it's a 2 by 2. These dimensions are not the same. They do not match, so the addition is undefined. It's not possible. We can do what's called scalar multiplication. If you remember vectors and scalars, scalars is just a number, no direction on it, just a number that we multiply by. So to do scalar multiplication, to do this right here, all you have to do is distribute the scalar inside to all the elements. So A says find 3 times big matrix A. So that means I'm going to do 3 times matrix A which is going to result in 6, 6, 12, negative 9, 0, negative 3, 6, 3, 6. So there's the answer for letter A. B says you're multiplying matrix B by a negative 1. There's a 1 right there, right? Here's like a negative 1. So in theory, all you're really doing is changing all the signs. So that's the answer for B. And now C says we're going to combine these two things together. We're going to take the answer we got right here, and we're going to subtract this answer right here. That's going to be letter C. So 6 minus negative 2 makes an 8. And 6 minus negative 2 makes that 8. I'm going to follow that pattern over and over again. 6 minus 0 is 6. 12 minus 0 is 12. Negative 9 minus negative 1 is really adding, so it's going to be negative 8. 0 minus 4 is a negative 4. Negative 3 minus a negative 3 is a plus 3, which makes a 0. 6 minus 1 is 5. 3 minus negative 3 makes a plus, makes a 6. 3 minus negative 2 makes a plus, makes an 8. So there's my answer to letter C. So scalar multiplication, super straightforward. So we don't have to just do scalar multiplication or addition or subtraction of matrices one at a time. We can do lots of matrices together. And all of these properties in this box up here are things that you have done in algebra for a really long time. A plus B is the same thing as B plus A. If I have A plus B plus C, I can do B plus C and then add A, or I can add A and B and then add C. If I do CD times A, I can distribute D in first and then multiply C in. 1 times anything is always the other thing. When you have a scalar out front, you distribute it into both matrices. And I can distribute the matrix across the addition of 2 scalars and do C times matrix A plus D times matrix A, and then I can add them together. So let's try. So the first thing, again, you always have to check is that the dimensions match. So if you look at number 4, all of these are 3 by 1 matrices, 3 rows and 1 column. Since all their dimensions match, then I know that I can go ahead and add these together. So on number 4, we check that all the dimensions match, and so I can just add these together straight across. 1 plus negative 1 is 0, plus 0 is 0, plus 2 more is 2. 2 plus negative 1 is 1, 1 plus 1 more is 2, 2 plus negative 3 is negative 1. Negative 3 plus 2 is negative 1, negative 1 plus 4 is 3, 3 plus negative 2 is 1. There's my answer. In the next problem, I can distribute 2 to both matrices, or I can add inside the parentheses and then distribute or scalar multiply by 2, which either one you prefer, you can do it. I'm going to do 2 scalar multiplication after I add together. So negative 2 plus 4 makes 2. 0 plus negative 2 makes negative 2. 4 plus 3 makes 7. 1 plus 7 makes 8. And then you multiply all that by 2 and get 4, negative 4, 14, and 16 is your final answer. So in our real number system, we have the additive property of 0, which means that you can add 0 to anything without changing it. We also have a matrix called the 0 matrix, which is full of entries of only 0, which has the same properties that it would do as 0 in our number system. So there is a thing called the 0 matrix, and it's full of zeros. So now we're going to solve a matrix equation, and it's very similar to what you would do in algebra. So this were an algebraic statement, 3x plus a equals b, and we knew what a and b are, or we wanted to just solve for x. We do 3x equals b minus a, and then we divide by 3, which means x equals b minus a over 3, which we can also write as x equals 1/3 of b minus a. So that's pretty much what we're going to do, but we're going to do it with matrices. So I have 3 times some matrix x, and we know that it's a matrix because it's a capital letter. So in math, when we use a capital letter for quantities like this, we know that it's a matrix. 3x plus matrix A equals matrix B. So my first step right here was to subtract that A over. So 3 times some matrix X equals negative 3, 4, 2, 1, minus 1, negative 2, 0, 3. These are both 2 by 2 matrices. They are square matrices, and because they have the same dimensions, you can subtract them. So I have 3x equals, and I'm going to subtract these. So negative 3 minus 1 is negative 4. 4 minus negative 2 is a plus, which makes a 6. 2 minus 0 is 2, and 1 minus 3 is negative 2. And then I'm going to divide by 3, or do what I said right here and multiply by 1/3. So I get x equals 1/3 of this matrix, which means matrix x equals negative 4/3, 2/3, 2, and negative 2/3. So up until this point, we have been adding and subtracting matrices and solely multiplying by what's called a scalar. Now we're going to work on some scalar. We're going to do some matrix multiplication. So when we added and subtracted, we had to make sure the dimensions matched. And now when we multiply them, we need to make sure that the interior dimensions match. So for example, if matrix A was an m by n, and matrix B was an n by p, when you put them next to each other and multiply in order, because the order is going to matter, we're going to do A times matrix B. If you look right here, you can clearly see that the n and n match up, and you're left with MP as the resulting dimensions of the answer. So order is going to matter, unlike it has normally. In matrices, order matters, and we need to make sure that the interior dimensions, the columns of A match the rows of B. That's the ends that I highlighted in gray, so that I can actually do the multiplication. So this may seem really tedious, but this is the way that I learned it, and I'm hoping that by color coding it and drawing it out, it works for you. So the first thing I'm going to do is make sure their dimensions match up so that I can get rid of the interior dimensions. So this matrix has 3 rows and 2 columns, and this matrix has 2 rows and 2 columns. And because the interior dimensions match, I can multiply them, and I'm left with what will be a 3 by 2 matrix. So to do this multiplication, what I always learned was I draw the matrix first, this empty 3 by 2 matrix. So this is going to be a 3 by 2, and I'm actually going to denote that it's a 3 by 2 by putting entries in. So this element A, actually let's use, I'm going to use I'm going to use ours because I have a matrix A and I have a matrix B. So this, actually, let's not use ours for resultant. Let's just use X's. So this element X right here is in row 1, column 1. This 3 right here is my rows. This 2 over here is going to be my columns. So then I'm going to have X row 2, column 1, X row 3, column 1. This is going to be X row 1, column 2, X row 2, column 2, X row 3, column 2. So those little subscripts are going to tell me what rows to go use. So because the rows came from this one, this is my rows matrix, and this is my column matrix. So if I want to go find this entry right here, I take row 1, column 1, and I'm going to get -1 times -3, this -1 right here times this -3 right here, plus this 3 right here times -4 over here, which is going to get me 3 plus -12, which results in a -9. So my first entry over here is going to be a -9. So then I'm going to do the next one. This next element says use row 1, column 2. So I'm going to do -1 times 2 plus 3 times 1. This is going to make -3 plus 3, which is going to result in a 0. Then I'm going to do this one. This is row 2, column 1. So you do 4 times -3 plus -2 times -4, -12 plus 8, negative. This one right here is row 2, column 2. So I'm going to get 4 times 2 plus -2 times 1. So it's going to be 8 minus 2, which is 6. So this entry right here is a 6. This 3, 1. So I'm going to use row 3, column 1. I get a 5 times a -3 plus a 0 times a -4, which is going to make a -15. And I'll use gray last. So this one right here is row 3, column 2. So I'm going to get 5 times 2 plus 0 times 1, which is going to make a 10. A 10. And so this right here is my answer. So my resultant matrix. So let's try the next one. So this is a 2 rows by 3 columns. This is 3 rows by 2 columns. 2 rows, 3 columns, 3 rows, 2 columns. So remember, my interior dimensions have to match, which they do, which means my resultant multiplication of 2 matrix. So I'm going to get a 2 by 2 matrix. So I like to draw that matrix out, and I like to list out the elements. This would be row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. And then I just match up what I said to what needs to be done. So I want to find this element. It says use, remember this first matrix is my row matrix. The first one is always the rows. And then this one right here, the second one, is always my column matrix. So if I do row 1, column 1. So I get 1 times -2 plus 0 times 1 plus 3 times -1, which makes a -2 plus nothing minus 3. So it's going to be a negative 5. This is row 1, column 2. So row 1, column 2. So 1 times 4 plus 0 times 0 plus 3 times 1 makes a 4 plus a 3, which is going to be a 7. This one right here is row 2, column 1. So you're going to get negative 4 plus negative 1 plus 2. Negative 5 plus 2 is going to result in a negative 3. This last one says row 2, column 2. So 2 times 4 is 8, plus negative 1 times 0 is 0, plus negative 2 times 1 is negative 2, makes this a 6. So this is my product of those two matrices. Oops, sorry. It's going to be a 2 by 2. So on the next page is just some properties of multiplication of matrices. Order does matter, but if you're doing A times B times C, it doesn't matter if you do BC first or AB first, but you have to keep them from linearly across in the same order. So ABC is still ABC in that order. It just doesn't matter how you group them. You can, if you have a matrix out front and you're going to add two matrices, you can either add them first and then multiply in or multiply together with the other matrix, or you can do matrix multiplication twice and then add the two resultants together. Similarly, the next one, because again, order matters, so we have to write it both ways, and they have to stay in the same order. So I can do A plus B times C, or I can do AC, BC, and then add the resultants together. I can also do AB times a scalar C. I know it's a scalar because it's lowercase. Or I can do the scalar times matrix A and then multiply in matrix B. Or because it's a scalar, I can do B times C and then multiply in matrix A. So all of those properties are helpful. Then we have the definition of identity matrix. An identity matrix is a square matrix where the numbers along the diagonal are 1. It's what we were trying to sort of get to in section 8.1 when we were getting that magic triangle of zeros in the corner. Because if we get 1s all the way down, then whatever this variable is, this was x first, then I can, if this were to become an augmented matrix, then I would know x's value right here. And if this was the y variable next, then I would know that y's value is right here. And if this were z, then this would be z right here. So that's called the identity matrix. It's like multiplying by 1. So in math, regular algebraic arithmetic math, if you were multiplying 2 times 1, it'd still be 2, because anything times 1 is itself. Well, any matrix times its identity matrix is still going to be the other matrix. And an identity matrix is always a square matrix. So we can't multiply a 3 by 2 times an identity because that identity matrix doesn't exist. An identity matrix only exists in a square form. So this is kind of what we were trying to get towards when you combine 8.1 and 8.2 together. I start up here with a system, and then I can write what's called the coefficient matrix. So here's all the coefficients. It's called matrix A. All the coefficients come from this side. Then the variables x1, x2, x3 become the variable matrix, which is called x. And this results in what the equation equals. And then what we did is we took that whole thing and kind of what's called augmenting it right here, and we made it one matrix. And then we were doing row reduction. And so when you do row reduction, this x is -1, y is 2, z is 1. You've solved the system.